Hello there. Today we're going to look at another paper in the realm of privacy and language models. This time we take care of text embeddings. The paper is called Text Embeddings Reveal Almost as Much as Text and is by researchers of Cornell University. The general problem is this: you have a piece of text like blah, 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 and you feed that through an embedding model, like any of the current text models that exist, and you get out a vector. Now, this is very often done. It's done for various reasons. For example, in something like Clip, you embed pictures and text together so that you can match the two in any text to image model. You first want to embed that text somehow. And in other cases, you send that vector to a database, a vector database, that sort of puts different vectors in different places, and then you can retrieve with a nearest neighbor retrieval. So let's say your query is here, you retrieve all of these things. This is done for sort of newer vector search databases, semantic search, and search across modalities. The question is, this vector right here, how much information does it really contain about the original text? If you know anything about these search databases here, you'll know that what they search are kind of more the semantics behind the text, especially if you do cross-modality search, like you search with text for images. You clearly see that they kind of embed in the space, embed kind of concepts and things like this. But the actual question is, if I just give you the vector, yes, you can search for concepts, but if I give you the vector, how much of the original text can you actually reconstruct just given the embedding vector of that piece of text? And the astonishing part of this paper is you can actually get pretty far, especially for short texts, without having the ability to backpropagate through the model. You are able to reconstruct the largest, like over 90%, or in the order of 90% of inputs exactly, or nearly exactly. And that is quite surprising. So we'll dive in. The paper isn't too long or too complicated, but I still think it's cool to look at it, and it's cool at what they've done. So they say they take a look at the problem of embedding inversion, which means reconstructing the full text represented in dense text embeddings. They say a naive model, if you just train a model to sort of take an embedding and output a piece of text, performs poorly. But a multi-step method that iteratively corrects and re-embeds the text is able to recover 92% of 32 token text inputs exactly. And that multi-step method here is the method they propose. I think they call it vec2text, and that's what we're going to look at today. They test on various things, and they test on a dataset of clinical notes. They say, you know, we can recover things like full names from that dataset of clinical notes, which is also fairly interesting, because if we assume that these vectors sort of represent concepts and things that they're trained on, you would expect that, you know, kind of the grammar and, you know, important nouns and so on are represented in the vector. But the fact that you can, even to a degree, recover things like names is quite astonishing. And as we'll see, some of the main effects here are going to be the fact that the text is short and the precision with which the embeddings are embedded. So all of this is not as clear when it comes to very quantized embeddings, which is often done, or when it comes to noisy embeddings, or, and that's also not something we've seen in this paper, maybe some sort of sparsification or dimension reduction is also excluded, at least for now, from this type of work. So all I'm meaning to say is that there isn't really super much evidence for these. This is only an initial step, which is still interesting. So their framing is mostly in terms of these embedding databases. So something like Pinecone, is a software as a service. You make a Pinecone database, you send your vectors there, and then you can search over them. Notably, you only send the vectors to Pinecone or to any of these vector databases. They don't necessarily need the rest. I think they'd be happy if you send them the rest, but they don't necessarily need it. You can just send them the vectors, and then you can query with a vector, and they'll tell you the IDs of the documents that you get back. So you never have to send the original text. And so that, for a lot of people, gives them a degree, at least, of privacy, if you will, where you can say, well, sure, they'll know what kind of concepts I have there, but they won't know the exact embeddings, the exact text. And this paper is obviously questioning that. So can the third-party service reproduce the initial text given its embedding? So they say, we seek to generate text such that the text is as close as possible to a given embedding. Our method, vec2text, uses the difference between a hypothesis embedding and a ground truth embedding to make discrete update to the text hypothesis. This, we're going to look in the next page at what exactly that means, what exactly their method is. But the result is that our method can recover 32 token inputs with a near perfect BLEU score of 97.3 and can recover 92% of the examples exactly. So what is their method? Their method is the following. What they want to do is they'll want to start with a hypothesis. So, I mean, I guess first it's important to note what they're given. They're given the embedding that they want to achieve. So imagine you are Pinecone, okay? You get an embedding from some user who sends you their vector. You get that embedding. And let's assume you also know what model was used to compute that embedding. Okay. If not, it's probably going to be one of 5 common ones, like it's going to be one of the OpenAI ones, or one of the Cohere or Anthropic, or one of the popular Hugging Face ones. So you can safely assume that for most projects, people don't actually fine-tune their own models, and therefore you just assume it's ADA2 or so. Okay, let's assume you know that. What you want to do with their method is you want to start out with an initial hypothesis. So the initial hypothesis you see right here. So you just start out with a guess of text that you then embed. Remember, you have access to the model that was used to embed. You can't backprop through it. Otherwise, you could just run some sort of adversarial attack through the model. But you can use the model to embed it. So you start out with a hypothesis, you send that to OpenAI yourself, and you get back the embedding, and that might come out to be here. Now, the first guess is going to be quite a crappy embedding. In fact, they show that if you simply train a model to input an embedding and output a piece of text, then that is going to not work too well. But that can be your initial guess. And then you have some sort of procedure to update that. So you start out with x0 or x hat 0, which is your initial guess. You embed it to get e hat 0, right? And then you observe what's the difference. And I mean that literally. What is the difference between the two embeddings, between the embedding that you got from your hypothesis and the actual embedding you want to achieve? And then you take that into account when generating the next hypothesis. So the thing here on the right is supposed to show you what is taken into consideration: the target embedding, the previous hypothesis, and the embedding of the previous hypothesis. In fact, not only that, but we'll come later to it, it's the embedding of the previous hypothesis as well as the difference between the two. And sure, the network could compute that internally, but you just make it easier by computing the vector difference beforehand. And from that information, the network can now update its guess. So it can change the previous hypothesis here and update it to get a new hypothesis. In our case here, this would mean that the previous hypothesis, the embedding of the previous hypothesis, the target embedding, and the difference between the two. They all go into some sort of neural network, and that's going to be some sort of T5 based transformer, which is going to give us the next the next hypothesis, x1 hat. We can then use the embedding model, which we have access to, right, to produce our next guess, which is represented here. And then we just do the whole thing again. So we take the new embedding of our hypothesis, we take the hypothesis itself, we take the target embedding, and we take the difference between the two. And from all of this, we're going to create x2 hat, the new hypothesis. And that, by embedding that, will give us the new embedding. Now we can even do cheeky things such as only accept the new embedding if it's actually closer to the target embedding than the previous embedding, right? If not, then we can just go back and sort of try again, try to come up with another new hypothesis and so on. So it's an iterative procedure to get us closer and closer and closer to the target right here. You could probably achieve the same thing by just kind of moving around, just trying to edit text and see what the embedding is, and then walk closer and closer and closer. It would just take a lot longer. Right? The hypothesis is that if your distance in embeddings is close enough, then you will have reconstructed the text. So that the hidden assumption is that there are necessarily no collisions in embedding space, which is probably fair as long as your input here is somewhat grammatical, right? Is somewhat in distribution for the embedding model and not just random nonsense. Yeah. So that's the procedure. Now, the obvious core part is we can train easily a model that produces that initial guess here, right? That initial guess, and my OneNote crashed. 1 second. All right, we're back. You can easily create a model that gives you this initial guess right here, right? All you do is you take any sort of data set of a text data set. You take a sample of text, you use the embedding model, which you have access to get the embeddings for that piece of text. You just do that a whole bunch of times, and you got yourself a data set of embeddings with corresponding text inputs. And at that point, you simply train a model to take in the embedding and give you out the piece of text. So that's easy. The hard part is obviously to come up with this editing model right here. So the model that goes and takes the previous hypothesis and so on, and the target embedding and the current embedding, and then comes up with a new hypothesis of what you should do. And, you know, ideally that new hypothesis is then better than the old hypothesis. They formulate this out right here, and I'm gonna jump a whole bunch of notes right here. But by the way, people ask me for these notes. Very few do, but these are a Patreon perk. That's like it's the only perk they get. But I don't know who wants my notes, honestly. But if you do, the papers are obviously all available, and they're linked in the description. So they formulate this out right here. They say, hey, if we have a target embedding and we want to generate the next embedding, this can be split up over the across the sequence of hypotheses. Every time we have to come up with the previous hypothesis, and then we have to edit that hypothesis to make the new hypothesis. And the editing process, so you can see this, all this marginalizes essentially out across this thing right here, and this thing is obviously a derived quantity from this thing. Yeah, here. So there's two components. One is the initial embedding, and one is this editing model right here. They say, okay, what we do is the following. We train the model by first generating initial hypotheses from the model in section 3.1. Section 3.1 is is just the simple model I described before, right? And then training a model on this generated data. So all they do is they take the model I just described here, the basic inversion model, then they take a set of embeddings, right? So you have like set of embeddings, 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 embeddings. You use this model here to create the approximate texts from those embeddings. So these would all be X zeros. Here I call them T zeros. But these would all be the initial guesses. And since you know what the original text was to do the embedding, then you have essentially all that you need. So this is this here. These are the same. You know the original text, you know the initial hypothesis, and from this you can also generate, by embedding, you can generate E0. So now you have everything that you need to train a model to generate the very first step of the procedure, right? Because we've trained a model to generate the 0th step, the initial hypothesis, and now we have all the data that we need to generate the first step. The first step being, I have an initial hypothesis. What should I edit it to? So you take a model that you input the embedding you want to reach, T0, E0, possibly the difference between the two, and you go for T, the original text. Now you can imagine this going on and saying, okay, this here will ultimately result in a model that, let's call that M1, where we call this here M0. This here will result in a model that can do that first step. What we can then again do is we can again take the original text, the original embedding, or we can take the original text. No, not the original text. We can take the original embedding. No, obviously we're going to take this text right here. I'm going to feed it through M. We're going to get the T1 hat. And then we can do the whole thing again, right? We can take this, the original text, the original embedding, and E1 hat derived from T1 hat, and create a data set to create M2. So a model that does the second step of the whole process. And we could do that for as many steps as we like. So essentially for each model for each step in the inversion process, creating a separate model. We've already seen things like this in diffusion, like diffusion models, image diffusion models, and so on. And people there, they have helped themselves by saying, instead of training one model for each step, how about we train a model that takes all of the inputs and then simply takes a parameter t here, lowercase t, that indicates the time step, right? T is 0 for the first model, t is 1 for the second step, t is 2 for the third step. And we just generate a giant data set and train the same parameters, but t is just a parameter. That works for diffusion models. In this paper, they go even simpler, and they just say, whatever, we just train that first step here. We just train this one. So we generate the initial hypotheses, and then we train a model to just, from the initial hypotheses, create the original text directly. And that's enough. Even for hypothesis number 5, we can use that model. Now, obviously, that doesn't really match the distribution that you'll get later on when you do the multi-step procedure that we saw over here, but it seems to be good enough for them, and it seems to work. And yeah, you always, like, the sneaky advantage you have right here is that you know the target, and you can always check whether the new embedding of the embedding of the new step that you've made is closer in embedding space than the old one, and if not, reject it. So you essentially have this very accurate guiding principle that helps you, and all that this model here has to do is give you variation like it's essentially, instead of walking around randomly in search space, it gives you an approximate direction to walk around, but you always have a very solid criterion to reject or to go towards. And therefore, this model doesn't need to be, you know, super duper duper good. And yeah, so it just needs to call down the search space enough. And that seems to happen. So that's what this paper does. It just trains a one-step procedure to reconstruct the original text. And then it uses that to nudge the text iteratively into a good direction. And according to their experiments, what's really important in this procedure is that you have these embeddings from the current hypothesis be part of the input, so that once you generate a hypothesis, you actually embed that hypothesis and get back where in embedding space you currently are and what the difference between the current embeddings and the target embeddings are, because that can help you a lot coming up with the next hypothesis. And without going through much of the text, that is almost all of the method here. Yeah, they have a paragraph against how exactly they put the embeddings into the form so that they would fit into a transformer. But yeah, to me, that's a bit of a technical detail. Now, the results here we've already gone over in the introduction, but essentially for data sets such as MS Marco, natural questions, for models such as GTR and the OpenAI API, they are able to reconstruct a ton of text. So you can see right here, 92% exact match, 97 below score. That's 50 steps of reconstruction plus beam search. So beam search tends to help a lot too. And again, right, it's a search problem with a very accurate estimator of whether you're on the correct path. And all you need is something to kind of guide you in the correct direction. And when you're able to reject stuff, if you go away, and you have a beam search that lets you kind of explore different paths to your goal, that is massively helpful. So it is surprising how much information there is in these embeddings, but at the same time, it's also not that surprising that if, you know, the information is there, you will be able to reconstruct it with a method like this. Still, the numbers are pretty high, and that's astounding. So here you see it works, but it works a bit less with the MS Marco dataset and the OpenAI API. I'm not exactly sure how many dimensions GTR has. Something that this paper doesn't really investigate is how the dimensionality of embeddings influences this, which would be interesting to know. What it does investigate a little bit is the length of the sequences. So here you always have 32 token sequences, and here on average you can see you have a bit more. And when you have a bit more, or when they make the dataset have a bit more, you can see that the reconstruction performance drops dramatically. You can still reconstruct stuff, but it drops, even though the cosine similarity of the embeddings, that is how cosine similarity is also very high. And yeah, that tells you that maybe for longer sequences, the exact text isn't as much represented anymore in these embeddings as for short text. Also here, you can see this table. This is now out of distribution. So the previous table, they have trained on these models, on these data sets, as far as I'm aware, or on the training sets. This here is out of distribution, so things they haven't trained on. And you can see the performance is still very, very good. So where the base model achieves 36 blue, vector text achieves 95 blue, and so on. But as we go down here and the sequences get longer and longer, you can see the performance dropping, being less. Not monotonically, but you know, kind of degrading as the sequences get longer, which is fine. And they're still much higher than the simple base model trying to one-shot invert the embeddings. So that is, and yeah, the difference is even more pronounced in long embeddings, right? The difference between the one-shot and the multi-shot. Yes, in domain, able to recover 77% of blue in just 5 rounds of correction. Out of domain is able to exactly recover 66% of examples. These are still really high numbers, right? So don't get me wrong here. They do an investigation into clinical notes, and what I found interesting is that they were able to recover 94% of first names, 95% of last names, and 89% of full names, while recovering 26% of the documents exactly. So even things like names, which you would expect to be, not as well represented in these embedding vectors, can be recovered with quite high accuracy. Now, one thing that could shed a bit of light here on what's going on is this investigation, which is really cool that they did. So what they said is, how about we add some noise onto these embeddings, right? Can we add noise and it therefore destroy the ability of any person or any attacker to reconstruct the exact text? Now, obviously, the answer is yes, depending on the level of noise. But as you up the noise, certainly at some point, the embeddings will have no longer the information to reconstruct the text. However, you have to select a level of noise so that they're still useful to the tasks that you want to do with them. And in this case, the framing of this paper, the task is vector retrieval. So they ask, is there a level of noise where reconstruction potential is low, but retrieval quality is still high? And the answer is yes. So you can see the intermediate level of noise here is where the reconstruction ability drops drastically, but the retrieval aspect stays high. And only later does retrieval suffer as well. So what I can imagine this means is that the vectors of embedding model, their lower frequencies, which is their more, meaningful components, if you will, they probably largely capture these more retrieval relevant semantic things and things that actually make a difference in meaning, whereas the higher frequency components may be used to store the minute details of the exact sentences. We've seen this also with image models and so on. Adversarial examples are bugs, not features, and things like this. A lot of places have discovered or reported on this, that models will use different parts either of the frequency spectrum or of the parameter space and so on to encode different types of information. And when you go start pruning and culling down or quantizing or noising things, you will not uniformly destroy information. And that's what seems to be the case right here. So the high frequency, minute details in the embeddings are probably representative of the exact text things, like, which exact token was used here and there. And if you destroy the high frequency part, and that's exactly what you do by adding Gaussian noise, right? It's like a convolution with a Gaussian kernel. You sort of smoothen everything a bit. You lose these things first. And yeah, that I find quite interesting. They make some other investigations, very interesting, all of that. So the last thing that I found interesting is that they experiment with this initial hypothesis, and they find that even if they put some random tokens, or they just put the word the, or they just put some sentence they found somewhere, it essentially works as well as if they generate the initial hypothesis with their base model. So their iterative procedure is able to very quickly escape from very bad initializations, which again speaks to the fact that they probably did well training that model, and it's completely fine to only train the one-step model, at least in this case. They have a few examples as well. However, yeah, there are a few, and they have a good section on limitations. One is obviously adaptive attacks and defenses. So the thing where they add noise, this is an explored topic in the area of adversarial examples, to just add noise, and that kind of destroys the adversarialness of any, or potential adversarialness of any examples. So if you get an adversarial example, or if you have a service where you classify images, you can just kind of add noise, and that will still allow you to classify it, but it will make adversarial examples be less effective. However, if an attacker knows you're doing that, they can take that into account when crafting the adversarial examples, and therefore, again, be very effective. So this paper doesn't investigate what happens if an attacker who wants to reconstruct text takes into account that there could be noise on the vectors. So that's for one. For the other, dimensionality of embeddings isn't really explored. Length is explored in a tiny bit of a degree, and if you think about it, then let's say, so they have 32 tokens here, right? 32 tokens into, what's the vocabulary size usually? The vocabulary size is like 32K, right? Which is like 2 to the 15. Okay, so there are, with a 15-bit, I have 32 times 15-bit. 32 is what, 2 to the, that's 2 to the 8? No, 2 to the 5. 2, 4, 8, 16, 32, 2 to the 5. Okay. So I have essentially a 32 token sequence is essentially 20-bit of information. Now the OpenAI ADA2 model is what? It has 1,530, something like this, right? So it's 64 times 24. No, yeah, I think so. Let's quickly check. 6. Yeah, that kind of makes sense. So they have, this is 2 to the 6. This is 2 to the 5. This is not 2 to the anything. So this is 6-bit, 6-bit. This is 2 to the 4.5. This is like 10.5-bit. No, sorry. That makes no sense. Because these are floats. So let's assume that for any reasonableness, we quantize. So quantization is also something that's not explored in the paper, which would also be really interesting to look at. What I feel, what I'm trying to get at here is that maybe, you know, there is some length where the embedding vector, just given by the dimensionality of it, is completely capable of holding all the information, even when you are very coarse in what you do. So let's assume we quantize to 4-bit, right? So each of these things actually has 4-bit of information, or 2-bit, right? Every position only has 4 different states. So let's say there's 2-bit. No, 2 is a bit rash. 4-bit. 16 different states. So there's 64 times 24 times 4-bit that can, you know, that are potentially inside of this vector. You can see already the difference here, I believe. Did I do something wrong? Maybe. Well, in any case, I feel for 32 token sequence, for 32 token length sequences, it's well enough to use an embedding vector of 1536, right? I mean, we can calculate in another way. What does it mean? It means essentially that you have 2 times 24, that's 48 dimensions per token. So every token has 48 dimensions that can potentially represent it, and you only need to index 32,000 things. So you only need 15-bit, but you have 48 floating point dimensions. Now we can calculate, what if this is 64? What if the length is 64? Well then, this here divides by 2. So you only get 24 dimensions. That already gets critical. What if it's 128? You only now have 12. And you have 12 dimensions to represent an index into a 15-bit set. And that's where it starts to get critical, right? And that's why probably once you go to 128, it starts to get critical, because you can no longer represent everything if this were binary. Now this is still a float, but as you go up here with the length, you go down here, and all of a sudden at 1024, you're left with only two dimensions, or one dimension or something like this. And with 2 or 1 floating point number, you're no longer able to represent this here. So you have to start to compress. And that's where we get the effect that maybe at those points, you're no longer able to reconstruct really exactly what happened there. Sorry for the bit of shady math, but my point essentially was that at 32 tokens length, you have plenty of dimensions per token to represent its index in a vocabulary. But the higher up you go with the sequence length, the more inconceivable that becomes, and the more you have to rely on actually learning grammar, learning frequencies, learning concepts, and so on, in order to bring down the loss during training. All right, math rant over. That was it for me for this paper. There's lots of more information in here, so give it a read, and yeah, I'll see you around. Bye-bye.